Today, we're going to dive into the hidden forces at work in still water. You know, everything from the immense pressure pushing on a dam to the simple, elegant principle that keeps a massive ship from sinking. Welcome to the world of fluid statics.
So here's our game plan. We're going to start with the absolute basics of fluids at rest. Then we'll unpack the really crucial concept of pressure. From there, we'll see how engineers actually calculate the incredible forces on submerged surfaces. And we'll finish up by exploring the science of buoyancy and stability. You know, why things float in the first place.
All right, first up, let's lay down the fundamental rules that govern fluids when they're perfectly still. So here's the key idea, and it's a big one. When a fluid isn't moving, things get a whole lot simpler. Just picture the layers of water in a glass. In fluid statics, those layers aren't sliding past each other. That means there's no internal friction, what engineers call shear stress. The only force we really need to worry about is pressure, which always acts straight on or perpendicular to any surface it touches. And believe me, this isn't just some abstract theory. These principles are what engineers use every single day. We're talking about designing the massive concrete wall of a dam holding back a lake, or even the small hydraulic jack that can lift your car. The principles of fluid statics are what make them work safely and effectively. Now let's zero in on the main character in this whole story, pressure. Okay, imagine the face of a huge dam. The water pressure is pretty weak up at the top, but it's immense down at the bottom. So instead of trying to deal with an infinite number of different pressure points, engineers simplify the whole problem. They calculate one single equivalent force, the resultant force, that has the exact same overall effect. So you've got this massive force, but where exactly is it pushing? That is just as crucial. This single point of action is called the center of pressure. If you get this location wrong, a structure could fail, even if you calculated the total force perfectly. It's the exact application point for that big resultant force. Now, in the simplest case, let's say gas inside a tank. The pressure is pretty much uniform everywhere, and when that happens, the math becomes really straightforward. The resultant force is just the pressure, P, multiplied by the surface area, A. And its point of action? Well, that's located right at the geometric middle of the surface, what we call the centroid. But that's for uniform pressure. So what happens in a liquid, where the pressure is always changing with depth? Well, it all comes down to one simple thing, vertical depth. The deeper you go in a liquid, the more fluid is literally sitting on top of you, and the weight of all that fluid is what creates the pressure. That's why it increases steadily as you go down, and that is the critical difference between liquids and gases in statics. And this is where we get this really elegant formula that captures all the physics. The resultant force, R, depends on a few things. Rho, that's the fluid's density. G, which is just the acceleration of gravity. A, the surface area. And finally, Y bar, which is the vertical depth from the surface all the way down to the centroid in the area. It's an incredibly powerful little formula. So this is basically the step-by-step process. First, you find the geometric center of your submerged shape, the centroid. Then, you calculate the pressure right at that central point. The total force is then just that pressure multiplied by the total area. But, and this is important, because the pressure is always greater at the bottom, the actual center of pressure will always be a little bit lower than the centroid. Getting this right is, and I mean this, absolutely critical. For a dam, that resultant force is trying to topple the wall over, and the entire structure has to be designed to resist it. For a submarine, the pressure is acting on all sides, trying to crush the hull. Mastering these calculations is literally the difference between a safe design and a total catastrophe. All right, so we've covered forces that push on things. Now let's talk about the force that pushes up and keeps things from sinking in the first place. You can really think of floating as a simple tug of war. The object's weight, W, pulls it straight down through its center of gravity, G. At the same time, the water pushes up with a buoyant force, R. This upward force acts through the center of buoyancy, B, which is basically the center of gravity of the water that the object has pushed out of the way. For that object to float, those two forces have to be perfectly balanced. But as anyone who's ever tried to stand up in a small canoe knows, just floating isn't the whole story, right? The object also has to be stable. And stability is simply the tendency for an object to return to its upright position if it gets tilted by something like a wave or a gust of wind. And this slide just nails the deciding factor for stability. It all comes down to the relative position of the center of gravity, G, and the center of buoyancy, B.
If G is below B, any little tilt creates a restoring force, a righting moment, that pushes the object back upright. But if G is above B, that same tilt creates a force that actually wants to flip it over even more, an overturning moment. So for naval architects, managing these 2 points is everything. They will intentionally add tons of heavy ballast low in a ship's hull for one simple reason: to pull the center of gravity, G, as far down as possible. This ensures that even in rough seas, G stays below B, creating that critical righting moment that keeps the ship from capsizing. It's a fundamental principle of safe design. So we've built a really solid foundation for what happens when fluids are just sitting still. But this, of course, opens up the next big question. What happens when we set them in motion? Because that's when brand new forces like friction and momentum come into play. And that takes us into the even more complex and fascinating world of fluid dynamics.